Good afternoon, everyone. Thank you all for coming. Thanks, Josh, for presenting on HydroBlue to us. So everyone's been hearing about it quite a bit recently. So I guess it's time to unpack it a bit for everyone.
Thanks, Elaine, for passing me over. So just, sorry, Prof, if I could just please share screen.
You can share now.
Okay, while I wait for that.
Yeah.
Okay, okay, great. So yeah, just to introduce myself, so I'm Joash, and just with my initial knowledge of geographic information systems, which is GIS, we came about with the HydroBlue project. And what the HydroBlue project was looking at is basically, can we create a model that allows hydrogeologists to identify the best locations to drill boreholes based on environmental factors. And what that actually has led to is us getting a better, or me getting a better understanding of geospatial data science. Sorry, in essence, what geospatial data science is that it's a subset of the data science, geographic information systems, and basic mapping capabilities. And what it actually allows you to do is it allows you to understand where and why things happen. So there are various different data formats within the realm of the spatial data science. The most commonly known is satellite imagery data. So that is actual satellite images taken over time, and image processing is done on that to identify what are the features behind that. Then in adjacent to that, you also get what are featured layers. So these are data that is captured over time in different regions. So for example, when you looked at HydroBlue and we were looking at how do we create a model that will show people the exact locations to drill based on these environmental factors, we decided to combine what is satellite imagery, which was the environmental data sets, and we basically analyzed the borehole data, which is a featured data set, which is captured by people over time. So a featured data set in our case, for example, is as people went and they drilled boreholes and they found out, yes, this is a functional borehole site, it supplies drinkable water, or no, it does not. That then populated what is the feature layer data set. So in essence, we had now both our satellite imagery and we had featured data. Now, when you work with spatial data science, the characteristic that actually defines it as a spatial data science project is the data must have geographic coordinates associated to it. So you must be able to capture what is an X and Y coordinate. So like I said, the field came about to understand exactly where things happen and why they happened. So it started with simple things such as, okay, we need to estimate where earthquakes are going to happen over time. And since then, the field itself has grown. So it started off as an earthquake warning system, the geospatial data science, and it's grown to other applications over time. Currently, the field itself has a 13.6% annual growth rate, and it's actually now worth 440 billion US dollars. So it's a very fast, rapidly growing field. And what essentially has happened is that people have learned to use the satellite imagery in a way that can benefit society for their needs. So while NASA and Google were collecting spatial data for over 20 years, they were also looking for ways to use them. So currently, if you look at what data sources are available, you can go to the Esri Living Atlas, you can go to the NASA Earth data, you can go to Esri's ArcGIS, who are global leaders in the field, and you can collect data from them that dates back about 20 years. So you can actually mine this data over time to understand patterns of behavior, spatial patterns of behavior. So just to get into it a little bit more, so I just want to just get into a little bit more. So what it actually is data over space. And so I just want to see, okay, and you guys can see my pointer. So it's data over space. So what happened is you'll find that so this was the original data set of borehole data that was available in South Africa, with the red representing problematic sites and the blue representing functional sites. And what we began to do was we began to basically plot this data or spatially join it to environmental data sets. And this is the first data set I put it on, which was vegetation. Now, as you can see, if you look closely, you'll find that within one polygon, so within one area, within one space, you will get both what is functional and non-functional boreholes. So this is a common problem within GIS, within spatial data science. And the way to overcome it is to basically combine it with various other environmental data sets that you believe may influence the overall outcome. So once we combine it, you'll find that those polygons get a lot smaller. And what happens is it creates a lot more diversity in the actual space and in the actual data set. So while, for example, you have so many both functional and non-functional boreholes in the space, by creating such a complex data set and complicating the environmental factors and creating a higher range of variety in it, you actually are then able to better estimate what leads to sustainable or not. So for example, if you had to put in your vegetation and soil type, this will split this one polygon into two. And what will happen is, although it's the same vegetation, it's the same vegetation with a different soil type. So it creates diversity for machine learning algorithms to identify what works and what does not. Now, I know that basically these terms are looking quite technical in terms of overlay joins and unions, and we will get into it a bit later on in the presentation. But for now, what these processing tools or these geoprocessing tools allow you to do is to spatially join data without a common field in the actual database. So I know with us and Python and with data science in general, when we join two tables, you need a common field to join it. Now, the advantage of spatial data science is you don't need a common data field, but you can join it based on its geometry and its geological locations. So going forward, so so what happens is generally with geospatial data sets, you see, because you display different layers over time, data is not collected at every X and Y coordinate in the country. So a lot of it is estimated and filled in. And what that means is that we have to then start using the Pandas database to clean our data sets. So when you get into it, you'll find that, and I just took a snapshot of the code itself here, but what you'll see is basically we are asking, so if it says true in this line of code, it basically means that these features have missing values. And then once you've identified the different features in the database with missing values, there's multiple ways in which you could clean it. So if you find that, sorry, and then I didn't put the snapshot here, but if you just change any to some, you can find out exactly how many rows of each item have missing values. So if you see, for example, that there's just one or two missing rows here, and you can afford to exclude those one or two rows in a database of which is about 10,000, you can afford to do that. You can simply drop, or you can associate NaN values to them. It depends on how you want to sort this. And yeah, so basically with geospatial data science, you are going to get imperfect data sets, and the data cleaning stage and the coordinate reference system features are extremely important. See, if this stage is not done correctly, then what will happen is you will get basically inaccurate analysis being done. So yeah, so like I said, you have cleaning. This is a big part of the spatial data science space. And the second part is you need to understand that the Geopandas library is actually built over what is pandas and NumPy. So it stores the geometry of data points in the data set and keeps the values that are generally associated with pandas and the NumPy. Now, it is able to both read and plot geospatial data. The important thing is that, you see, when it's plotting geospatial data, you have to ensure that it's the same coordinate system used on all your data sets. So for my project, for example, I may have received the vegetation in one coordinate system. I may have received borehole data in another coordinate system. And a large step in terms of creating a data set that could be joined and analyzed was to change this accurately, to all move it all to one uniform coordinate system. And in our country, in South Africa, there is a law passed that every department has to spatially capture its data. So that is a bylaw that is available. So all fields are captured in data spatially. It's a question of whether you can get it. But the problem is they are using different platforms. So when they use the different user interfaces, like I said, this kind of messes up the coordinate system. So the way I went about doing it, and this is just a snapshot of the Python code I used for HydroBlue, is you see where in this Geopandas library, just to identify, so SDF was my actual data set. And what I did was I specified that my latitude and longitude, and if you look in the data table, this is the latitude and longitude, and I printed it. Thereafter, I query to find out what is the actual coordinate system used. And you'll find that this was the coordinate system used. If you need to, oh sorry, and then after I plotted it. So once I plotted it, I could see, you can actually see the shape of South Africa. You can plot it on a world map, but this is basically just me plotting over South Africa. And you could plot and you could see, if you look carefully, you'll find that the light blue points are actually those are the functional boreholes, and the dark blue are the non-functional boreholes. This is more insight into the coordinate reference system. So before you join any two data sets, you have to print this out, read and engage with it to understand that it's using the exact same coordinate systems. Because if you plot one layer on top of the other incorrectly, the spatial analysis will not work. It's either Python will return back null values, or the analysis simply does not work. Then you also have ways in which you can change it to other coordinate systems if required. So to move on, so the most common coordinate system that I used, or I prefer to use, is this WGS84, and that's for the reason that it accounts for the Earth's size, shape, the gravitational pulls, and it accounts for the different fields. But you find that it's because of the nature of my study that I chose this coordinate system. If you look at something like Google Maps, they're using this coordinate system, which doesn't really require you to understand the shape of the Earth or the gravitational pull at this time. So it all depends on the type of study that you are doing and what coordinate system would best suit you. So, and that's fine. Okay, then just to go a bit into the more technical terms. So like I mentioned, so the spatial joins and the spatial data sets, what that basically means is that we are able to join and match data sets, like I mentioned, on geometry rather than on unique, the same fields or columns within a table. So this will be your first feature, for example, this will be a second feature, and you want to find out what happens, or you want to pull out this. So you want to know, like for example, for me, I wanted to know when I joined, I wanted to put my borehole data points within the environmental data sets and the polygons for the environmental data. And then there's many ways in which you can do it. So you can say, for example, I want to do a spatial join that shows me what data is within another data set on a map. You can say what data intersects with other data sets and it only pulls out those values, or what data basically is contained within a data set. Then you also get simple things such as a buffer analysis. So quite often, like when I did my hydroblue study, I needed to know all of the characteristics in a large space or an area in time. But you see, a buffer analysis could also be applied, for example, say, I know like some of you guys were talking about those health apps and those exercise apps, and you got a route. So say, for example, you got a route and somebody's running along it, and you don't need to know everything that's happening in the whole of Durban in that route. You just need to know maybe what is 2 kilometers from that. You need to know, for example, what are the high risk areas. You need to identify maybe the psychological or physical barriers to that. So it's used very much so for proximity analysis. And this is something I haven't done for my study in particular, but I know that a lot of your studies or your projects or things you're thinking about, it may apply to this. And then it's based on what they call centroid values. So at the heart of every polygon, there is a value associated to it. So it works from that center point, and you create the buffer from there. So you could, for example, play with the size of the data over space or data over time, and you could basically work along those lines. Then yeah, so then basically you see, if we look at the spatial operations, and this is a feature that I used quite a lot to create the diversity in my data set. So what it does is it superimposes one data set onto another. So if you look at the image here, if you look at the image here on your right, you have your base map, which you started with, which is just showing you the different regions and your coordinates and stuff. Then you get to put in all your other features, one on top of the other. And then as each feature is put on top of the other, it creates new polygons, smaller polygons. And I brought ours down from, I think it was a radius of 1:500,000 to about 1:15. So just by adding different data sets, so I added about 15 environmental data sets, and I managed to bring that down. And quite often, I know when we had presented HydroBlue, people had asked us, what's your rate of accuracy? And then I went back and I checked. So we started off 1 is to 500,000 and brought it down to 1 is to 15. Also, in different, it differs by region, but an average of 1 is to 15, smaller in some cases. So that basically means that when people are looking to drill, the system will identify within like maybe a 5 meter radius, which is not a lot for groundwater when identifying it. And yeah, so it's quite a high level of accuracy. And your overlay analysis and like I said, it's one of the most important things if you are going to be working with geospatial data science. And if you look at, so once this is done and you create a data set like the one I had for HydroBlue, it then at this stage becomes possible for you to apply different machine learning algorithms. And then you can create what is your different patterns of behavior. And I'll just show you guys a bit of the code very quickly just after this, before I get into the next one. So I'm just sending again. Okay, so this is okay. So this is the one that I created just for today, and you guys can see. So yeah, so first I pulled out what is the data set that we had created for HydroBlue. So as you can see here, we have our active status of true and false. So that tells you whether a borehole is functional and supplying quality water that is drinkable to people. Then you can see, for example, we've had things like your yield, your erosion risk, your sediment yields, your groundwater usage over different areas. There were quite a few more vegetation type. Altogether, is about 15.
Sorry, Joash, we
Yeah.
can't.
Sorry, Vinod, we can't see what you're looking at. We can see a Udemy screen saying overlay analysis.
We can't see your screen much. Okay,
Can't see my screen. Okay,
we can
one second. Can you see now?
We can see a Jupyter notebook now
Right,
with some
great.
results.
Okay.
Cool.
Okay, great. So as you can see, basically, here you see what I was speaking about, which is your active, which is your true and your false. So this represents what are both functional and non-functional boreholes. And then if you go across here, this is your mean average rainfall, your yield, the status of your yield, and it goes on. Then if you look here, as I explained earlier, we had that true and false to tell you where there were missing values. And here you could actually see the sum and the count of that. Thereafter, okay, this is just a shape. Just 1 second. So this is when it begins to plot. So you see, it's not a very complicated code to actually bring the map in. And although there are many different user interfaces that can plot the data, this is kind of going back and it's taking out the dependencies on the different interfaces like the Google Earth Engine, the Esri ArcGIS, the QGIS, and it's allowing you to plot in code itself. And then, yeah, so basically, if you look here, so this was coordinate systems. And what I did here is, you see, when I got this coordinate system, it didn't plot correctly. So this is the different point data, the borehole data that was given to me. It didn't plot correctly, it was plotting somewhere in the ocean. So what I had to do was, I had to put in a statement that forced its coordinate system and forced it to understand exactly where it needs to go. And then once I plotted it here, you find that it plotted in the right coordinate or the right space. Sorry, that's just table cleaning. Then the same happened here with the environmental data sets. And what had to happen here was the same thing, because when I had tried to join these two data sets using a spatial join, it kept on saying to me that the coordinate systems were not aligned. So that's when I realized that, I had to kind of go back first and rework all of coordinate systems before I could join the two data sets. So if you look at the first one, so this is all your environmental factors in here, your evaporation range, your vegetation types. This is your borehole data. And then you find that when I had done the spatial join, you'll find there's no common field in it, yet it managed to perfectly join the two data sets together. And then you have this one integrated database that now the different machine learning algorithms can be applied onto. So in terms of my study now, we have applied the different machine learning algorithms, and it's actually showing accuracy rates of about 90% around there. So we did use a few. I think one of them we used was nearest neighbors. And yeah, and then in terms of the way forward for me is that, you see, I mean, in terms of this seminar series, what I will do is I will show you guys how to apply all of the different spatial analysis algorithms. So not just the machine learning, there are a few other algorithms that can be applied in geospatial data science. Thereafter, I'm working on a data visualization system to basically create a user interface, bring the map in. And yeah, at the end of it, the end product of this geospatial data science solutions is an interactive map that basically people can query just by panning across screens and clicking in different locations. And it provides you with what is a pop-up box and a pop-up feature. So yeah, so that's my way forward. And yeah, I hope this session was informative for you guys.
So, Mr. Chair, maybe you could unmute yourself and invite people to ask.
Sorry, Prof. I saw you unmuting yourself. I didn't want to speak over you. I apologize. Thanks, Joash. Thanks for the presentation. I know I was making notes throughout while you were going on, and yeah, I think now is the question and answer period. But I'll wait until the end to ask my question. So, does anybody other than me have any questions? I think you guys can go for it.
Yeah, I just have a question. I know, you know, Joash, you spoke a lot about this, you know, satellite imagery, and I think you said NASA, Google, I don't know, Esri as well have been putting up data. But how accessible is that data? Does it have a cost? Do you have to buy it? Is it a subscription? Just wanted to get an idea on the accessibility of this type of data from your experience.
Okay, so we've actually have connected to all of these guys through API calls. So the Google Earth Engine, NASA Earth Data, and Esri Live in Atlas have APIs, and you can access their data for free. But okay, so you can access their data for free, and it all is available. You see, it depends what data you're looking for. If it's considered to be non-strategic, which all environmental data is considered to be, then you will be able to easily access it. But you see, you get free data through those API calls, and then you also get paid data. So the paid data does cost more, but its level of accuracy is far higher. So while I brought that down to maybe a 1:5 scale, I mean, if you get the paid data, it'll be brought down even further. And in fact, there are quite a few competitions and calls and stuff that are available. So once you kind of have some project and you can see that, then you can apply for one of those competitions and you could win that data in a sense, like free access to that data. So the data, in terms of if you want just a broad perspective and a general overview, a lot of that data is available for you.
Okay, all right, thanks. And the APIs that you speak of, I'm just assuming here that I think the data providers, do they provide like the code for the API, or do you have to create your own?
The API code, most of it I would say is published. I mean, I managed to get it just by going through their documentation, the system documentation of all of the different companies, and I can share that with you guys. I mean, I do have that after all my research, but yeah, so it is like you just have to learn how to interact with it a bit. But I mean, in terms of to make that connection, it's quite simple.
Okay, all right, thank you.
So if I can come in there, yeah, before I ask my question, just on that APIs question, yeah, it's an important one for everyone here to be able to do. And I think the best way to learn about APIs is to actually create one. So all of us have our projects where we are doing some processing of that data, and we all want to share that method out with the world, right? We all want to develop our model and host it on a server and enable someone else to have access to that model. And the way you grant access to your model is by creating an API. And you typically use something like HTTP or HTTPS, use one of those protocols so that you web enable access to that. And in fact, it will be a facility of this group that you'll be able to host your Python code in the cloud and enable API access to it. So I think that's something we almost need to make a feature about, and it relates to security issues and so on, because at some point you'll want to manage your access. You won't want to give well, in some cases you'll be able to give public access, but for some cases you'll want to restrict access to, for example, your subscribers and so on. And then that introduces the whole problem of authentication and security and all those things, which are each academically interesting as well. So it's worth making a thread out of that, a series out of that, if anyone's interested. Yeah, can I ask my question as well there? Okay, I was just interested to know about this, you know, the WGS84 coordinate system. I don't know if that's the right term, coordinate system, but where you mentioned it accounts for the gravitational field. Yeah, I was just wondering what that meant specifically.
Okay, so where it accounts for the?
When you said it accounts for the gravitational field and electromagnetic field, and there were a good few other things. So when you say it accounts for that, like, what does it do? Does it reshape the area somehow, or yeah, what does that mean?
Okay, 1 second. So yeah, so basically what it means is, if you look at this slide, 1 second, I'm just going to put it on. Okay, so if you look at this slide here, then what happens is you see a lot of so you get the maps are projected differently. So when you look at this coordinate system that this coordinate system here, this WGS84, it would plot on what it would look at the Earth and the sphere kind of shape, as opposed to on just a 2D map that is printed, which is the bottom image. So if you look at the second one, this is looking at what is like on a flat map, while this understands that it's more of a globe. So that's, if that answers the question.
Yeah, in a way, I got that part, because I know that different maps, yeah, the areas change quite a lot for the different styles of maps. But I wasn't too clear how gravitational fields were also factored into that.
Okay, so that's fine. So what it basically means is based on the data. So if you're using that type of data, then this would be the best coordinate reference system to use. So it doesn't mean that it's kind of it's not something that is automatically included into this coordinate system. But if you were to use that type of data, this is the best coordinate system to use. So that's why I said it depends on the type of project that you are doing.
Okay, thank you.
All right. Thanks for that, Prof. Does anybody else have any other questions? I mean, you guys can raise your hands.
Yeah, Joash, you mentioned you use nearest neighbors. So when you were saying that, what do you feed that algorithm? Do you use the coordinates, or do you use other parts of data? How do you get how do you use nearest neighbors to find where the closest ones are?
I think what we did was, if I'm not mistaken, I think what we did was we used the X and Y coordinates. So, and we used the status of the borehole as functional or non-functional, and we trained the model using that. So on the X and Y coordinate, they also existed the different environmental factors. So it wasn't just 1 second. So if you look here, what you can see is on this X and Y coordinate, when you clicked on it, the status came up, which is active, which was true. And then you could see all of the different environmental factors on that. So we use the X and Y coordinate and the status as the main yes and no. So the so the status of the borehole as functional or non-functional was the yes and no feature, and it was based on the X and Y coordinate.
Sorry, on that, Josh, was it not about the input space rather than the geolocation space? Because wouldn't you look at the, like if you're looking at rainfall and vegetation, those inputs, so the neighbors in terms of those values and how well those cluster, whether or not it's a good or bad borehole. So it's not only about geolocation; it's also about the input feature space.
Yeah. No, correct. So yeah, so the input features are all accounted for at that X and Y coordinate. So in and around. So so for example, okay, so for example, so this was one, and when I clicked on it here, although I'm querying by X and Y coordinate, it's returning to me the different input features and the outcome, which was that functional and non-functional boreholes.
Yeah, why I was asking is because there's lots of other algorithms. I know Prof and I were working on a couple where we take in a lot of different inputs to try and cluster things together. So I was just wondering, do you just use coordinates? Because you mentioned you have quite a bit of input information. So you are using all of them to try and pinpoint exactly where you're looking to sort of find your borehole.
When we train the model, we put in all of the different inputs, so all the different environmental factors, and then we did the feature selection from there.
Well, I think it's a good question, and it's something for us to actually understand in the group. It's an important thing to understand, which is if you provide too many input features, then your groups become too granular. So you sometimes you see you don't want to group these things by geolocation. I would say your geolocation is just your reference for you to pull the right numbers so that you're talking, when you're trying to put data together. I would say that's the only thing geolocation matters for. You are just trying to get the right numbers in the right row. But in terms of the features of the row, in terms of the features of the row, that state space, you probably want to strip geolocation out of that because, for example, if you have rainfall, let's say you have, let's just say 20, right? Never mind what it means. So if you have lots of regions of rainfall 20, then you don't want those subdivided because they are in different regions. You want to say, it's of the same rainfall type and the same vegetation type. So that's one row. So there's an important point here, which is in terms of developing your model, you don't want to, how can I say, disaggregate that data too much. You don't want to cluster. You don't want to create all these clusters on variables that don't actually matter to the model. So that's something to be wary of in developing those machine learning models.
Okay, cool. I think okay. We'll check over it.
Okay, a quick one, Joash. So you said the data goes way back in history, and then when you overlaying all your layers with soil type and demographics, obviously as the years go, that changes quite a bit. So it can skew your data how far back you use it. So how do you deal with it? Like, do you take? I'm not sure. It was just a thought.
You can query it in terms of, no, I only want data from 2018 or 2020.
Okay.
So you can query, just the data is available. It's what you pull from the API.
So for your purposes, is it best to just take the latest information, or do you need something?
That's what I did. That's what I did. I did take the latest available information.
Okay, cool.
So yeah.
Just to add to that point, what you can do as well, if it's going to be time series based, maybe you can look at, because I know from my experience, natural phenomena, they're sort of seasonal. They sometimes have a seasonal trend, because it can be an argument. They can ask you, okay, if you're just using the latest data, what if it changes, in the future years? So one thing you can do is maybe you can just look at how, for example, a particular, the rainfall pattern over the years, whether there's a significant change in that, and then, for you to just, prove whether, the values that you have. And if there is a seasonal pattern that is there, then there are some methods that are available for you to sort of average, weighted average across the season, the seasonal trend. Yeah.
Okay, yeah, I guess you could, yeah.
Sorry, if you let me come in on that one. I think that's another important one, and it relates actually to the previous point from Samishka about, you see, I would say in that case, you shouldn't average that out. I would say what you should do in that case is actually, you should actually use time of year as another variable, because that's rich data. If you go and average out over the whole year, you are likely losing a lot of valuable data there. And then sometimes maybe you don't want time. So what you could look at is you could break that down into 4 classes of time. And there are ways to do that so that you retain the right amount of variance. Or you can look at some features, like you can fit a polynomial to it, and then the parameters, you can break that down to 2 or 3 parameters, and then those become your features. So yes, sorry, that was just, I wanted to relate that to that previous point.
I think Faisal, I think you have a question. Hands up.
Yes. So Joash, this is my understanding of your process, and correct me if I'm wrong, right? So you're accessing multiple data sources, refining that data, integrating those data sets, and performing spatial analysis of that data, right? Using machine learning algorithms. So my question is, what are the expected outcomes from that analysis? So what are you learning from this that assists you in finding good borehole locations? And the second part is, what are the other possible applications of this data analysis?
So yeah, I think when we had initially done it, we just used the machine learning to identify locations where you can actually drill and strike groundwater. Because the main challenge that was that we were trying to address was there were a lot of dry boreholes being drilled. So as the project has gone on, we also are looking at other inputs now. So when we had spoken to people like WRC, one of the things that came about was, like, can you identify areas with excessive nitrates? So there are now other output features that we are looking towards. Then there was also, for example, people were looking for agricultural usage. So I know that they want to find out, for example, this may not be drinkable, but maybe we can use it for some crop or something like that. So the end product right now, I mean, at this stage, is to create a model that says, yes, there's groundwater, or no, there's no groundwater. And then what happens is, from there, there's continuous development to find out then what would be the quality of that water and possible alternate uses for that water supply.
So how do you come to the conclusion that there is groundwater in a specific area? Just give me
Okay.
simple case.
Sure. So the way we did it was, you see, I collected a database from the Borehole Association of South Africa, and they provided us with borehole data, point data, and the status of that borehole. So wherever the status of the borehole is true, it means they struck groundwater, and wherever the borehole status was false, then it means that the borehole was dry, or there was some problem in that with the actual water access there. So that's all we've used so far.
Okay. And in terms of locating more viable borehole locations?
That will be based on the different environmental factors and the input values that led to the sustainable boreholes or the functional boreholes. So it's like we created the model based on that data, and then we have environmental data and all those input data throughout the country. So there, from that point on, yeah, we will use the environmental factors to say this generally leads to sustainable or functional boreholes, and it will identify the location.
Okay. Thanks.
So I think I don't think anybody else's hand is raised. But does anybody else have any questions before I go? None. Okay, cool. Joash, thanks for the presentation. That was very informative. I heard a lot about it, but this is the first time I actually learned about it. I think the first question I want to get into was the image you showed on the slide where you have multiple geographic layers with different data sets and types of information that are overlaid basically on one another, to increase that accuracy, I think quite significantly. I think you said from 1:500,000 to 1:15 or whatever the case may be. Um, how do you actually incorporate the level of influence which these different layers have on your accuracy? So what I mean by that is, for example, if one of the layers is what's the existing water table at a particular region, that would be a primary, like something that's a core indicator to borehole viability. But if another example would be vegetation, so how sparse or how densely vegetated is the area, that's kind of like a secondary indicator of groundwater or whatever the case may be. So how do you incorporate kind of like these levels of viability of these layers into your code?
So you're talking about like how did I know basically what to include as input features initially, and then in the second phase was obviously feature selection. Once the machine learning algorithms were applied, then we narrowed it down. But initially, what I did was I looked at the indicators that hydrogeologists generally look for when they drill boreholes, and I looked at the Water Research Commission and the study they had done, and what like data they were collecting, what were they looking at. So I didn't go and randomly put what I thought, in a sense, that people should look at. I looked and I put in the different data that I know that hydrogeologists look for. So that was the first step. And then once we applied the machine learning algorithms, we did do a feature selection, and we also reviewed that and had a look at it. And basically, it's also about what made logical sense to us. So we looked at the different features, and like things that popped up were like the average rainfall and vegetation, the yield potential, the groundwater usage. Like those were the common things that popped up. So yeah, so that's the way we actually went about doing it.
Okay. All right, cool. And then I remember, when Faisal asked about uses and stuff, one of the things that popped to my mind, which I'm not sure if you thought of, there's a company known as Mosgas, and they do offshore dredging, where they're trying to figure out what's the best location to kind of have these pipelines for gases, obviously used for fuel that are below the seabed. So this could possibly down the line be, in some way applied to that particular type of application. But that's just a thought. I think we all thought about the data mining over time, and there's people asked a few questions there. But my question over there was, if you're mining data over time, and especially with South Africa being a third world country, and when you're cleaning the data from the tables, is there a way for you to know that if you have data from like a really long time ago, maybe where the sensors weren't as technologically improved accuracy wise, as they are today, or whatever the case may be, and then if you're cleaning data points out of your table, how do you ensure that that accuracy, you're not removing valuable data points, but there's some that you have to remove which are inaccurate? So how do you go about doing that?
Okay, so firstly, so South Africa itself doesn't have time series data. It's the Google Earth Engine and the NASA Earth data, and that data is based on satellite imagery, and it's based on their sensors, and they have automatically eliminated. So if you look at certain factors, they all don't date back to 20 years. Some of them date back 5 years, some of them, it depends. But the time series data is from them. As far as our country goes, they collect data more in that feature layer format that I told you about, where it's actual data points and work they've done. So they spatially capture those things. So yeah, so that's, I don't know if that answers the question.
Yeah, no, I just wanted to know, because there's some regions in South Africa where it's like very, very sparse. So I imagine the data wouldn't be too reliable if we were collecting it. Then just a final question on the actual database, because you were talking about database joins, and Prof knows that I've been spending some of my time toying around with some of these things. I don't understand, because I think you use Geopandas, so I don't understand too much about this tool in particular. But I think at the one point, if I remember correctly, you said that you kind of ran code to see if there was a join between two databases, but the databases were exclusive of each other. Is that correct, or
Yeah.
am I not remembering?
No, so what happened was, you see, if you look at the image, so this image here, what you will see is that you can literally put one on top of the other. So imagine one map going on top of the other. And what happened was, that's why I said if the coordinate reference system is not correct, then Python itself and the Geopandas library will give you an error.
Right,
So,
right.
so basically that's what was a problem. But it's spatially, when I say spatially joins, I mean it understands geometry and it understands where each thing is located. And you
Oh,
can
okay.
join based on that, and it creates a new ID in the data set for you.
Okay. All right, cool. Because I was thinking like database table joins and inner joins and stuff. It's a different thing. Okay, cool. Yeah. So yeah, I think I'm done with my questions. If anybody else has anything else to add, we have about 10
Sorry,
minutes left.
sorry, Sudain. I think the way to look at it is, yeah, it's not a SQL join of tables. It's not like you are joining fields across tables. It's more like interpolation. So you are interpolating across data sets. So they all and it might be that one layer has a different coordinate system to the other layer. So there's a bit of translation to do as part of that interpolation. So Geopandas has these nice routines baked into it to make all that easy and seamless.
Okay. All right, cool. Thank you, Prof. Thanks, Joash, for answering my questions and everybody else's. Yeah, guys, we have 9 more minutes. So if anybody else has anything else to add or Joash wants to elaborate on some things, go for it.
Hey, I thought I would ask, because I was supposed to ask Joash this on the side. Prof, I haven't had a chance, but I think I'll just take this opportunity to ask him now. So, Joash, I just wanted to find out, here at work where I work, if you want access to GIS, like they need to like allocate some license to you and they give you a dongle and whatever. But you must be working specifically with GIS. So I don't have that access. What I wanted to ask you is if you like, how do you get access to GIS if you just need it for like research? Like how maybe like I'm looking at seeing what building types of information they have on there. So how would I get access if I can't get it from here at work? And like, yeah, basically.
Okay, so the SD Pro license is something we took that was about 2000 Rand. It's a user-friendly interface, and there's a lot of documentation and stuff on it if you need to use it. And there's also QGIS, which is an open source software. So your best option will be QGIS. And like I said, both systems are very well documented. So it's quite simple to actually get them or get functionality on how to use them.
Okay, no, thanks.
Okay, thanks. Yeah, does anybody else have anything to add or any comments?
Maybe just a note to current and future chairs. We normally reserve some time to give feedback on the presentation itself. But I think in a case like this, with so many good questions, I would rather have more good questions like this than presentation. But it might be something you want to just ask the person presenting. If you want, maybe in a private chat or something, just ask, would you like time for presentation feedback, or you happy to go with more questions?
Okay, cool. Yeah, I think if nobody else has anything pressing that they want to ask, I think Joash, just with the same slide that we're on with the spatial operations, with the overlaying, with my personal project, I think I'd like to learn the algorithm that you used, to go about this overlaying process. Because so in my personal project, I'm working with kind of introducing semantic relations and kind of links between not just databases, but stringing words together, kind of a thing. So in a way, the same model which I'm looking at, I can kind of visualize that it would be applicable to my own work. So hopefully when you get a chance to, I'd like to have a word with you about how you went about doing that.
Okay, that's fine for my side. We can pick that up.
Yeah. Okay.
Okay, so Chair, if you want to close the paper, then I'll close the session from there.
Yeah, I think that's good. All right, cool. Thanks, Joash, once again for presenting. It's very informative. And if nobody else has any other questions or comments, I think we're done here.
Great, thanks, Chair. Can I ask Pilani, who's up next, please? Who's on next week?
Next week is Mopedi. He confirmed that he will be available to present on the 27th of October.
That's great.
So I'll be getting his an abstract from him this week, and then I'll send an email out to everyone.
Okay, that's great. Also, I don't know, I guess just in the 5 minutes left, does anyone want to suggest any changes to our format? Or, normally we do that kind of thing at the start of the year, and I don't really remember us doing it this year. But, this format, is everyone happy with this? Yeah, okay. So everybody's kind of head banging, so that's good. Okay. Okay, then I guess that's it. Thanks very much, Josh, and thank you all. And we'll meet again, I guess, Friday/Tuesday. Okay.
Cheers. Bye, everyone.
Bye.
Cheers.
Bye, everyone.
Bye, guys.